In the previous problem, in the previous part, we have done the first portion of this problem. That is, we were successful in finding the resultant force created by this non-uniformly distributed loads, and we said that the resultant force has a magnitude of 160 Newton. Now the question is where this force acts. I said that the force acts at the centroid. Now, how to find the centroid? The question is, we said the force acts at the centroid. The question is how to find the centroid of an area. The formula for the centroid of an area is, see, the formula for finding the centroid of an area is, okay, is we write it as x bar is equal to integral x dA integral x dA divided by integral dA. This is the formula for finding the centroid of an area. We find mathematically, we find centroid. The definition for finding the centroid is x bar, the x coordinate of the centroid, is equal to integral x dA divided by integral dA. Now, as first of all, what do we mean by this dA? dA means you have to divide your load diagram into small strips, into small areas, whose area will be very, very small, equal to dA. That's what we did previously. This was our load diagram. From this load diagram, we divided into small strips such that the length of the strip was very, very small, dx. And this length is, since this length is very, very small, okay, this strip, this small strip can be considered to be a rectangle. Therefore, the area of the small rectangle will be equal its y coordinate, that is w, multiplied by its length, that is dx. W into dx represents the area, small area of our strip. Okay, whenever we have to find the centroid of an area, we again have to divide, like we did in the previous case when we are finding the resultant force, dividing the diagram, dividing the load diagram into small areas, and we said that this area is equal to dA is equal W into dx. Therefore, we write here, as far as our dA is concerned, this is a small area we have selected, we have drawn on this load diagram, and we say as far as dA is concerned, this is equal to W into dx. Okay. Now, what is this x? As far as x is concerned, x is the x coordinate. X is the x represents the x coordinate of this small area dA. How far away the is dA? This is our dA. This can be represented by a line because the thickness dx is very, very small. How far is our dx from x-axis? Oh, sorry, from the origin. Okay, this, the location where you have taken your dA is how far away from the origin. What is its x coordinate? We have selected that let its x coordinate be equal to x. So our x is x, our dA is w into dx. Therefore, we can write in this formula our x coordinate of our area element, we have selected x, and as far as our w dA is concerned, our dA is equal w multiplied by dx. Okay, since in this numerator dx is the variable of integration, x varies from x is equal to 0 to x is equal to 2 meter. So we'll write the limit of integration is from x is equal to 0 to x is equal to 2 meter. Okay, so it means divided by integral dA, and we know integral dA is equal to dA is equal to w into dx, w into dx. Okay, w into dx. Again, x is the variable of integration. X varies from x is equal to 0 to x is equal to meter. Okay, so this integration, this integral we can solve this integral over here. Let me solve it over here. We can solve this as, this can further be written as, this integral can further be written as integral x going from 0 to x going to 2 meter, x going to 2 meter, x and w is our 60x square. Let me put units with this. It is 60x square, 60x square, and we have dx. Okay, wx dx divided by integral of 0 to 2 meter, 0 to 2 meter. W is 60x square and dx. Okay, so that is equal to perform the integration, 60 will come out. So this is x square into x is x cube. Integral x cube is equal x raised to power 4 divided by 4, with limit of integration going from x is equal to 0 to x is equal to 2 meter, divided by 60 will come out. Integral x square is equal x cube by 3. Limit of integration is from 0 to 2 meter. That can be simplified as, we can simplify this to, this is equal to, this is this 60 and 60 will cancel. This is this can be written as x raised power 4, limit is from 0 to 2, that is 2 4 8 16, 16 by 4 divided by 8 by 3. Okay, that is equal to, see, this is meter x raised power 4, so this is 2 meter, so this the once you are raising it power 4, it will be meter raised power 4, and this will be x cube 3, that is 2 meter cube, that will be meter cube will be here. So meter cube and 1 meter will, you will get answer in meter. So that will be 16 by 4 multiplied by 3 by 8. Okay, that is 4 ones, 4 fours, so that is 4 ones, 4 twos, that is 3 by 2, that's equal to 1.5 meter. Okay, so you got x bar, the x coordinate of the centroid is how much? They got the x coordinate of the centroid is equal to 1.5 meter. Now join the two solutions, that is, in the previous part we obtained the force of 160 Newton, and in the second part we obtained that it acts at a distance of 1.5 meter. Okay, so from the origin go to a distance of, from the origin go to a distance of 1.5 meter. So we are here at this 1.5 meter distance, apply the force of 160 Newton. Okay, so this completes our problem. So you see, we had a non-uniformly distributed load. This load we replaced by a single load of intensity 160 Newton, and this load was acting at a distance of 1.5 meter from the origin. This is how we have to solve these types of problems. Now, in order to understand, in order to answer to part 1, why we said that the resultant force acts at the centroid, the answer to that lies in the formula for the centroid itself. If we look at this formula, x bar, we said it is the x coordinate of the centroid. And x coordinate of the centroid means, we have said that centroid is a point where the resultant force acts. Okay, and as far as this denominator is concerned, integral dA, our dA in this case is, in our case, dA is equal to W into dx. W represents the intensity of the load, Newton per meter. Dx is in meters. Meter cancels. This dA represents the small force which is created by the small area element dA. Okay. Now, when we are integrating this dA, so I mean to say that dA represents the small force dF, which is produced by the small area dA. Now, integral dF represents the total force or the resultant force. Now, if we cross multiply, we will have x bar integral dA or integral dF, because dA in our case is small force dF, is equal to integral x into dA, which is in our case is equal dF, small force dF, because small area dA represents the small force dF. Now look at this formula. This formula is the balance of the moments. This formula is the balance of the moments. It says, as we did in the previous case, when we had concentrated loads acting on the structural or the machine component. Now, if you look, this is balance of moments. Balance of moments means x bar into dF. This is the moment of the resultant force. dF represents the resultant force. Okay, dF represents, integral dF represents the resultant force. Resultant force multiplied by x bar is the moment of the resultant force about an axis passing through point O. That is, this line, this part of the formula represents the moment of the resultant force about an axis passing through point O. Now, as far as this df, integral df is concerned, as far as this x into df is concerned, df is the small force acting at a distance. Df is the small force acting at a distance dx. X into df represents the moment of the force df about an axis passing through point O. But once we are integrating it, it represents the total moment of the force about an axis passing through point O. It represents the total moment of the force about an axis passing through point O. It means when we are using this formula for the centroid formula is same as the formula we did in the previous problems. That is, we have to place this resultant force at such a position such that the force will produce the same moment about an axis passing through point O as the moment produced by this non-uniformly distributed load about an axis passing through point O. That's why we are taking the centroid for that's why we are saying that the resultant force passes through the centroid. So in next classes, we will be finishing up few more concepts, few more problems of solving the uniformly distributed loads or non-uniformly distributed loads. Thank you very much.